Ever try to clean out a really narrow tube, like one that goes crazy deep?
Oh, yeah.
That's the challenge with Proppant Cleanout in oil wells.
I can imagine.
And today we're diving into how machine learning is, well, making this process faster, more efficient, and maybe even safer.
Yeah, keeping that balance of pressure and flow, it's critical to avoid damaging the well, you know?
Exactly. We've got excerpts from this technical paper presented at the Mediterranean Offshore Conference,
Okay.
and it really gets into the details of how these machine learning models are actually built and tested, and
Interesting.
how they perform in like real-world scenarios.
Oh, wow.
By the end of this deep dive, you'll understand how this tech can predict bottom hole pressure with, honestly, impressive accuracy,
I bet.
giving engineers a real leg up in optimizing cleanout operations.
That makes a lot of sense.
Before we get into the weeds, though, let's
Yeah.
give our listener a little 101.
Sure.
What is proppant even?
Okay, so proppant.
And why is cleaning it out such a big deal?
So when a well is fractured, to increase production,
Right.
a fluid carrying these tiny grains of sand called proppant is pumped in.
Okay.
These grains, they hold open the fractures,
Okay.
allowing the oil and gas to flow more easily.
So it's like keeping the pipes open, basically.
Pretty much.
Yeah, okay. Got it.
But over time, this proppant, it can build up and actually start to, hinder production.
Oh.
So that's where proppant cleanout comes in.
So it's like a super delicate plumbing job, but like deep underground.
Yeah, kind of.
What were some of the challenges then with the old school ways of figuring out bottom hole pressure during these cleanouts?
Well, traditionally, engineers, they relied on downhole gauges for those direct readings.
Okay.
Or they'd have to do these, super complex pressure drop calculations
Oh, I bet.
based on, nitrogen injection rates and surface pressure.
Lots of numbers.
Yeah, and those calculations, they were super time-consuming.
Oh.
Needed tons of data and often even needed, calibration.
So machine learning basically swoops in to offer a faster, more efficient, and probably more accurate alternative.
Yeah, that's the idea.
What kind of data did the researchers use to train these models?
So they collected data from 48 wells in the western desert of Egypt.
Okay.
The data set included, depth,
Okay.
coiled tubing dimensions,
Uh-huh.
bottom hole temperature,
Right.
gel and nitrogen rates,
Okay.
surface pressure,
Got it.
and of course, those bottom hole pressure readings.
A whole lot of information.
Oh, it was, yeah.
But raw data can be messy, right?
Definitely.
How did they, prep this data for the machine learning models?
Right. So that's where data pre-processing comes in.
I was going to say, you got to clean it up.
Yeah. They cleaned the data, first of all, removed errors,
Yeah.
outliers.
Okay.
And then they normalized it
Right.
using this technique called min-max scalar.
Okay.
Make sure all those parameters are on, a comparable scale, which is key for those models to learn effectively.
I feel like we need a little more on min-max scalar,
Yeah.
what it does and why it matters here.
So imagine you have parameters measured in completely different units.
Like feet, Celsius, and PSI.
Exactly.
Okay, yeah, that makes sense.
So depth in feet, temperature in Celsius, pressure in PSI.
Right.
Min-max scalar basically converts all those values to a range between 0 and 1.
So it's like putting them all on the same playing field.
Yeah, exactly.
Okay, got it.
This helps the model recognize patterns and relationships that might be hidden by those original units of measurement.
Oh, that makes sense. So once the data was pre-processed, how many machine learning models did the researchers build?
Well, they actually created 9 different models.
9.
Yeah, to really explore a range of approaches and see which ones perform the best.
So they were thorough.
Yeah, this level of thoroughness is really important in machine learning research. You want to make sure you're picking the most robust and accurate model for the task.
9 models. That's dedication. I'm sure they didn't just take the model's word for it.
No, man.
How did they test and validate their accuracy?
Okay, so they used 2 pretty rigorous validation methods.
Okay.
The first was K-fold cross-validation.
K-fold cross-validation.
Yeah, think of it like dividing the data into 10 groups.
Okay.
You train the model on 9 groups, then test it on the 10th.
Got it.
They repeated this 10 times, each time with a different group as the test set.
Do they really mixed it up?
They did. And to make it even more robust, they repeated the entire 10-fold cross-validation process 10 times.
Wow, okay. They really put these models through the ringer.
Oh, yeah.
What was the other validation method?
So the second method was repeated random sampling.
Okay.
Kind of similar to, k-fold cross-validation.
Mm-hmm.
But instead of dividing the data into equal groups, they randomly split the data into training and testing sets.
Right.
But they did it multiple times.
Okay.
This helps ensure the model can handle variations in the data.
Makes sense.
And it's not like overfitting to a specific subset.
So 2 different approaches, but the same goal. Making sure those models were as accurate as possible.
Exactly.
Could all 9 models, like, ace the test?
Well, not exactly. The top 5 were the neural network, AdaBoost, random forest,
Okay.
K-nearest neighbor, and gradient boosting model.
So those were the, like, all-stars.
Yeah, you could say that.
Okay.
These models all had like incredibly low mean absolute percent error, MAPE, values.
TPE.
Yeah, they range from 1.6% to 3.2%.
Wow. That's really good, right?
Yeah, it's pretty impressive.
Any standout stars among those top performers?
The neural network model really stood out.
That's the one we hear about all the time.
Yes, yeah, it's popular for a reason.
Uh-huh.
It got a correlation coefficient, RO, of 0.947, meaning it was, exceptionally good at predicting those actual bottom hole pressures.
Okay.
You really nailed it.
That's a crazy level of accuracy. But, how do we know this isn't just, like, theoretical?
Right.
Did they actually put this model to the test, like in the real world?
They did, yeah.
Okay, good.
They applied the neural network model to an actual well.
In the Western Desert.
Yeah, they called it Well X in the Western Desert of Egypt.
Well, X.
They took the well's data, all those
Yeah.
parameters,
Okay.
coiled, tubing depth, temperature, gel and nitrogen rates, surface pressure,
Right.
and they fed it all into the model.
What happened?
Drum roll.
Mm-hmm.
The model predicted a bottom hole pressure of 4208 psi.
Okay.
The actual pressure, what they recorded downhole, was 4138 psi.
So close.
Right. That's a difference of only 70 psi.
That's tiny.
Yeah, like a mere 1.7% error.
Wow. Okay, so that's incredible.
It is.
Such a small difference when we're talking pressures that high. It seems like this, could make these clean-out operations way more efficient and maybe even safer, right?
Yeah, absolutely. Being able to, predict bottom hole pressure with this kind of accuracy, it could lead to faster cleanout operations.
How so?
Well, you're not constantly having to adjust parameters based on guesswork or, delayed data,
Oh, okay, yeah.
It's more streamlined.
So faster operations would mean less downtime and, ultimately more production.
Yeah, exactly.
Okay.
And it's not just about speed either.
No.
Accurate pressure prediction also reduces the risk of, damaging the wellbore during the whole cleanout process.
Oh, right.
Damage to the wellbore can mean costly repairs and lost production. So this technology has, big implications for cost savings as well.
So it's a win-win.
Yeah, seems that way.
Were there any, unexpected findings, things that came out of this research that they weren't really looking for?
Well, one of the most interesting findings was from the sensitivity analysis they did.
Okay.
This helps determine, which parameters have the biggest impact on the model's predictions.
Okay, yeah.
Sometimes parameters you think would be super influential turn out to not be such a big deal, and vice versa.
Oh, interesting.
It's kind of cool, right?
Yeah.
It can help engineers understand those complex, relationships in the cleanout process and lead to new optimization strategies.
So it's not just a black box, this machine learning model.
Right.
It's actually a tool for learning even more about the system itself.
Exactly. That's one of the most exciting things about this tech. It's not just about prediction, it's also about discovery.
I love that. It's so cool how those two things are connected. So we've covered the data, the models, the validation, and the sensitivity analysis.
Yeah.
Let's talk about how this would actually be used. How would an engineer use this machine learning model during an actual proppant cleanout?
So imagine you're an engineer on site, right?
Okay.
At a well that needs a proppant cleanout.
Got it.
And you've got this machine learning model all set up, either on a computer or integrated into the coiled tubing control system.
So as the operation's going on, you're monitoring things like, coiled tubing depth, gel, and nitrogen rates, surface pressure, all that.
Right.
All the usual stuff.
So you could use this model, in real time to make decisions during the operation.
Yeah, exactly.
Oh, wow.
You feed that real-time data into the model,
Okay.
and it gives you a prediction for the bottom hole pressure.
Okay.
And then that lets you make smarter, more proactive decisions about how to adjust the operation,
Okay.
keep that pressure right where it needs to be,
Right.
and avoid any problems before they even pop up.
That's really smart. It's like having an AI assistant
Yeah,
helping optimize the process.
exactly.
But new tech like this usually comes with a hefty price tag.
Yeah.
Is this only for, like, big companies with deep pockets?
That's a good question. It's true that, cutting edge stuff can be expensive at first,
Yeah.
but the whole field of machine learning, it's becoming way more accessible now.
Yeah, there's open source libraries,
Okay.
cloud computing,
Right.
and more data scientists out there.
Uh-huh.
It's making it easier for all kinds of companies, big or small, to try this stuff out and adopt these tools.
So it's not just a futuristic concept then.
Right. It's something that could benefit the entire industry.
That's awesome.
Yeah, and as the technology gets, more refined and adoption grows, we should see even more innovative
Yeah.
applications, and probably prices will go down over time.
So it's like a really exciting time to be in this field. We've talked about all the potential good stuff,
Uh-huh.
but are there like any downsides
Well, of course.
or challenges?
Yeah, with any new tech, you got to be aware of the potential pitfalls.
Right.
One of the biggest challenges in machine learning is needing those like huge, high-quality data sets to train these models.
Makes sense.
If the data is incomplete, biased, or just wrong, the model's predictions aren't going to be reliable.
So garbage in, garbage out. What are some other potential challenges? Data quality is super important for these machine learning models.
Yeah, totally.
What other potential challenges should we be aware of?
Well, even with like perfect data, you still have the risk of overfitting.
Overfitting.
It basically means the model gets too specialized to that training data,
Okay.
and then it might not work well when you give it new data, stuff it hasn't seen before.
Oh, so it's like a student who memorizes the whole textbook,
Yeah,
but can't actually use the ideas in the real world.
exactly. That's a great analogy. You got to find that balance
Okay.
between teaching the model to see those patterns,
Mm-hmm.
but also making sure it can work in new situations.
That's tricky.
It is. It's a bit of an art, really.
It sounds like there's a real skill to developing and using these models the right way.
Oh, absolutely. You need that data science expertise,
Right.
but you also need to know the industry
Hmm.
and understand, what the model can and can't do.
We've talked about the good stuff, the importance of good data, and this whole overfitting thing.
Yeah.
Anything else our listeners should keep in mind?
I think the biggest thing is that, machine learning is changing so fast.
Right.
What's cutting edge today might be old news tomorrow.
Yeah.
Got to stay on top of things.
That's true for anything, I guess.
It is, yeah.
But especially in machine learning, it's moving so quickly.
Absolutely.
Hmm.
And, with any powerful tool,
Uh-huh.
you have to use it responsibly.
Ethically.
Yeah, ethically. Make sure these advancements are actually helping people
Right.
and think about those unintended consequences.
Yeah, that's a good point. Sounds like we've got a lot to look forward to.
I think so.
The future of machine learning in energy and, everywhere else.
Oh, definitely. This is just the start. As we get more data, better models,
Sure.
and really understand how to use this technology,
Right.
the possibilities are endless.
This has been a great deep dive. I think our listeners got a much better grasp on how machine learning is changing Proppant Cleanout and what
Mhm.
that means for the whole energy industry. Any final thoughts?
I hope this has gotten people curious and excited about machine learning.
Yeah,
We're in the middle of a tech revolution,
it's true.
and it's amazing to see how these advancements are solving real problems in such cool and unexpected ways.
Well said. On that note, I think we'll wrap things up.
Okay.
Thanks for joining us for this deep dive into the world of machine learning and Proppant Cleanout.
Thanks for having me.
We'll see you next time for another look at, cutting edge tech and how it's shaping the world around us.